Okay, welcome folks to another Cosmic Conversations. We're here virtually in your house, not Morrison Planetarium. My name is Josh. I'm one of the Morrison Planetarium staff, and I am honored to be here today with our science expert, that is Dr. Brian Day.
Good morning. How are you, Josh? And hello to everybody else out there.
Indeed. For those of you tuning in live, we are thrilled to have you here. If you're tuning in later, watch the whole video. It's going to be a cool one. We are here with Dr. Day to look at our lunar surface in open space software and talk about some of the really cool things that we still have to learn about our moon. So with that, I'll hand it over to Dr. Day. I'm going to be piloting and asking questions, but if you have something you'd like to know, drop it in the comments and we will do our best to address questions either now or after the video is done. Here we go.
Thank you very much, Josh. Well, everybody, welcome to the moon. We are right now experiencing the 50th anniversaries of the various Apollo missions. And so we're looking back at those, but we're also looking forward because we're planning to go to a whole series of new destinations on the moon that will tell us far more about the history of this fascinating object. Back in 2018, NASA held a meeting specifically looking at places that we would want to go. And so we're going to take a look at a few of those today. So with Josh at the helm here, we'll start out by flying to a formation known as Reiner Gamma. And Reiner Gamma is an area that shows up as what we call an albedo feature, an area of contrast between light and dark. It doesn't really have any topography. It's really quite flat. But what you see here is this swirl-like pattern of light and dark, very sinuous. And this also happens to be an area where there is a localized magnetic field. The moon no longer has a global magnetic field the way the Earth does, but it still has localized magnetic fields in certain areas. And this is one of those. And what we think is happening here is that localized magnetic field is channeling and directing charged particles from the sun and elsewhere. And as this radiation comes in and bombards the surface, you get effects of space weathering. But because we have these channelizations of the magnetic field, you have certain areas getting more and certain areas getting less. And so you have this change in the weathering from one area to the other following these magnetic field lines. It almost looks like what you'd see sprinkling iron filings over a piece of paper overlying a bar magnet. Very fascinating.
Paintbrush effect too.
Isn't it? Yes. And of course, the question is, well, what is causing this localized magnetic field? We don't know. That's one of the reasons why we really want to go there and check it out. So this is a fascinating area. This is Reiner Gamma.
And this really has a big chunk of lunar history built into it.
That's right.
All these volcanic features date back pretty far.
So you're actually leading into something wonderful. This does overlie a volcanic feature. And so we're going to kind of zoom in next and see, well, this is the Marius Hills region. And this is one of the most spectacular concentrations of volcanic cones on the surface of the moon. And you look at this here and you go, not so spectacular. But we're going to change our view from the wide-angle camera aboard the Lunar Reconnaissance Orbiter now to a laser altimetry view. And we'll let that tile in for a second here. And this will give us a completely different view of this. Here they come. And you can see that there are, probably something close to 200 volcanic cones and domes here. They stand out in the laser altimetry view, but not in the photographic view. That's because these are really very subtle, low-profile objects. The reason they are so low profile is because of the nature of lunar magma. Most lava that has erupted on the surface of the moon is very low in silica content. It has very low silicate levels. And that means that it also has very low viscosity. Lava with greater levels of silica in it tends to be pastier. But this stuff, when it erupted, most of the lunar lava erupted with a viscosity of about olive oil at room temperature. And it's hard to build a mountain out of that.
So
but
where would
here,
people on Earth be familiar with silica?
So we can take a look at the differences. Well, first of all, silica, one great example is go to the beach and look at sand there. There's a great example of finding silica in a form you can pick up in your hand. But in terms of silica and volcanism, if you think of the difference between, say, going to Hawaii and looking at the low, broad shield volcanoes there, that's, again, lava that is very low in silica. Whereas if you go to something like the Cascades or the Andes and you have the tall peaks there, now you've got higher silicate contents and the lava erupted as a thicker, pastier thing. But what we see here when we look at the Marius Hills is an area where apparently volcanism happened over a very prolonged period of time. And so we would love to get samples from this area and be able to see how there's been an evolution in the thermal and chemical processes of the lunar interior. So these are the Marius Hills. And then we're going to proceed a little bit north from there to the Aristarchus Plateau. This is a spectacular area. You've got the craters Aristarchus and Herodotus down at the south edge of the plateau. But the plateau itself is really a volcanic wonderland. And you'll notice that big, long, sinuous rill there. That is Schroeder's Valley, the widest and deepest of the sinuous rills. It almost looks like a river valley, but no water ever flowed there. It was carved by flowing lava. And the eruptive center at the head there, it's sometimes called the Cobra Head. If we switch to the WAC view here, we'll get kind of a different impression. We can see why it's called the Cobra Head there. And that's about 10 kilometers across. So that's a big eruptive center. But then you'll notice those kind of darker stains all around the plateau. And those are deposits of pyroclastic ash. So you had fire fountain eruptions going on here. Apparently eruptions that were very rich in volatiles that caused this fountaining into the sky. And when we look at some of these pyroclastic deposits, they seem to be actually relatively rich in water content, water trapped within those beads of volcanic glass, perhaps several hundred parts per million. That could conceivably be a resource for us. So a lot of interesting things going on the Aristarchus Plateau. And yes, this is one of the places we are considering for future landings. So our whole idea here with what we're doing today is we are touring candidate future landing sites. And we're going to continue north and a little bit east from the Aristarchus Plateau. And we're going to go to the Gruithuisen Domes. And this is a trio of volcanoes that stand out very differently from what we saw before looking at the Marius Hills. Here we don't need to switch to laser altimetry. We have these two big domes and another smaller one up above, you can see. And these stand about 1,500 meters tall.
Wow.
These are very different than what we had seen before. And when we were looking at the Marius Hills, these are big, tall, relatively steep volcanoes. And looking at the spectra from these, we see that again, this is a much more silicious, it's got a lot more silicate composition in the lava that was erupted here. Why would the lava here be so different? We don't know. Again, one of the real... Yes, that's right. We want to go to the places that are confounding us. And as you'll see, we've got more of that coming. So this is a fine example of something that we need to try to understand more. And for, I think, even a more profound example, let's jump to the Aina Caldera.
So this is going to be a little bit of a flight all the way to the other side of the moon. And Dr. Day, can you mention, this looks a lot lighter than the area around it. What's going on here?
So what we're doing here is because of the fact that the Aina Caldera is actually a small feature, it's only 3 kilometers across. And so what we have done here, Josh has overlaid on top of our big global mosaic from the wide angle camera aboard LRO, he's now overlaid a view from the Lunar Reconnaissance Orbiter's narrow angle camera, which gives us much finer resolution. So we've overlaid this high resolution view from the NAC, the narrow angle camera, so that we can see the fine details in the Aina Caldera. So what we have here is a volcanic caldera, again, about 3 kilometers across. And as we look at it, we see this really weird morphology. We see these kind of low blister-like formations that are, maybe 10 meters tall. And then we see this weird rough terrain between those blisters. But if we look at that rough terrain between the blisters, one thing we don't see are impact craters. That's really interesting because we use impact craters as a gauge, as a measurement tool to estimate the age of real estate that we're looking at on the moon. Fresh territory will have few impact craters, but as time goes by and meteoroids slam into the moon, you'll start getting more and more craters appearing. And ancient terrain will be very heavily cratered. But here, between these blisters, we see almost no impact craters at all. And if we were to do a little math and figure out the rate of cratering versus what we see here, we're getting that this territory here is probably on the order of 100 million years old or less. That's a problem. Because our understanding of thermal modeling of the moon is such that all volcanism should have stopped a long time ago, more closer to 1 billion years ago. And the idea that you could have volcanic features that are perhaps only 100 million or even tens of millions of years old, that is a little confounding for us. So we're trying to figure out just what is going on here in the Aina Caldera. Aina is an example, just one example of this type of formation that we call IMPs, these irregular mare pits. And we're not sure what's going on here.
Are there a lot of other similar features, these irregular mare pits?
There are a number of these, yes. And we're just, another example is, I'm blanking right now. I'll come back to it. There's a famous rill that has a volcanic crater. On the floor of that volcanic crater is, and another great example of one of these strange imp features. But while we're talking about pits, let's go to the Sea of Tranquility. And in the sea, of course, the Sea of Tranquility is famous for having been the site of the Apollo 11 landing. But there's also a really magnificent feature here, and you'll see, once again, Josh has provided us with a high-resolution view here from the narrow-angle camera. And what we are going to do is zoom down to a mare pit. This is an example of what appears to be a skylight. We're looking down into some sort of a cavernous void beneath the surface. What we think may be happening here is we're looking at a collapsed roof to a large lava tube beneath the surface. We see similar things here on Earth quite often. And so you could have had lava flowing across the surface that got crusted over on the top, still flowing beneath. The lava flows out, leaves this large hollow tube, and then eventually part of the roof collapses, exposing an entrance to this great cavern beneath. These could be very interesting. They could potentially harbor volatiles, be places where things like water and other volatiles could be sequestered, could accumulate beneath the surface. Some people even talk about these as being potential safe havens where our astronauts could retreat under these layers of rock, especially if you've got an issue of a solar storm. So these are truly interesting areas.
So, Dr. Day, I'm seeing down at the bottom of the pit some irregularities. Are those probably chunks of the roof that fell in?
Yeah, we're seeing boulders down there.
That's amazing.
So and the neat thing is, as you look at this area from different angles, as the Lunar Reconnaissance Orbiter was flying over, you can, depending on where the shot was taken from in orbit, you can see under the rim in one direction or under the rim in the other direction. And so we realize this is not just a cylindrical pit going down. This actually does have lateral extension going off to the sides.
Good amount of real estate down there.
Yeah, it's pretty wild. Now, everything we've been looking at so far has been on the near side of the moon. This is the side that faces us. But there's, of course, wonderful stuff going on the far side. And so I see Mike Murray has a wonderful question about the far side. And so, Mike, we will answer your very question in just a bit. But first, we're going to fly to one of the most remarkable features of the lunar far side, and that will be the South Pole-Aitken Basin. Pictures of the moon always look gray, Joan mentions, and or won't. And yes, they do. The moon is largely shades of gray. Now, there really are subtle colors there. There are greens and browns and blues, but very, very, very low saturation. And sometimes you'll see people will be able to boost the saturation. But for the most part, with your eye, the moon does look to be shades of gray. But there really are these very, very subtle colorations. And through a telescope, even a small telescope, you can start to tease those out. So the South Pole-Aitken Basin is the largest impact structure on the moon. It is 2,500 kilometers across. This probably nearly disrupted the moon, this impact. But when we look at the far side of the moon, it's really kind of hard to tease it out. That's because it's also a really old feature, and it has been battered by lots of crater impacts subsequently. But if we switch again to a laser altimetry view and kind of colorize it so that we color code different altitudes, we'll make blue really low and red high. And if we do that, we'll see the South Pole-Aitken Basin will stand out for us.
It's coming, I promise.
Yeah, it'll take just a moment for the system to load it, but here it comes.
Boy, nothing makes you miss the computers at the academy like doing this stuff from home.
Yeah, it's a little challenge. There we go. So you see this big dark blue area surrounded by higher terrain. This is the South Pole-Aitken Basin. It's about, again, 2,500 kilometers across, 13 kilometers deep. This is probably significantly over 4 billion years old,
Wow.
dating back to perhaps what we call the late heavy bombardment, when things were really active in the solar system. We had a lot of crashing going on. And
this could be one of the biggest impacts, right?
Yes. This is, again, the largest we see on the moon, and it is certainly one of the largest in the solar system, perhaps one larger on Mars that we know of. But this is really spectacular. And it could be an anchor point for us in our understanding of the lunar chronology. So we would really love to get some of that material in hand and precisely age that, provide a precise date for this impact. But also, one of the things we would like to do as we explore the moon is, yes, we'd love to explore the surface, but we want to explore the interior. And just as here on Earth, one of the things you love to do is you'd love to drill down into the mantle and sample mantle material. Well, drilling down into the mantle here on Earth is a really hard thing to do. On the moon, it would be even harder. But fortunately, nature may have done that for us with this titanic hole in the far side of the moon. And it is quite possible that the impact that carved out the South Pole-Aitken Basin may have actually excavated mantle material. And so again, that's something we would love to go and collect. Now, on the edge of the South Pole-Aitken Basin is a somewhat newer large crater, and that is the crater Schrodinger. And Schrodinger is a fascinating area. It is a multi-ring, or it's what we call a peak ring basin. So as we look at craters, we see them kind of changing morphology by size. The smallest craters are simple pits. The larger craters end up having a central peak. And think of kind of a rebound happening. And even larger craters too, that central peak turns into a central ring like you see here, a ring of mountains. Now, this is a fine example of that type of structure. You have wonderful outcrops of basement rock. You have mare deposits. So you can see the bottom of the floor of the floor of the crater there was flooded by subsequent eruptions of lava. And as we zoom in, there we can see these fractures going across the floor there. And right along that one fracture that Jake just, right there, we have a beautiful volcanic pit crater. So yes, most craters on the moon are impact craters, but here's an example of a volcanic crater. And you notice the dark terrain around that, how it's stained darker than the rest of the areas. That area right around that volcanic pit is darker. And that's, again, a blanket of volcanic ash. So, Mike Murray, yeah, absolutely. On the far side, we do see volcanic features.
Now, so Dr. you mentioned there's a, I might be jumping a little bit out of order, but another one that you can see the dichotomy between the near side and the far side.
Yes, so there is a definite dichotomy between the near and far sides. On the near side, we have the mare, the seas, very prominent. Those areas that have been, where the large impact basins have been flooded by subsequent eruptions of lava. On the far side of the moon, you do not see that. You still have the large impact basins, but the crust on the far side of the moon is thicker. And so you did not have as much of that flooding of Mare basalts on the far side. Now, why is the far side crust thicker than on the near side? We don't really know. That's a subject of debate. Now, here we have a fine example of a beautiful multi-ring impact basin. This is the Orientale Basin. And this straddles right on the edge between the near side and the far side. And you can see that this basin here is only partially flooded. In the center there, you can see floodplains of basalt, but you can also see how there's still quite a bit of structure, this multi-ring structure that is exposed here. You get this almost beautiful concentric bullseye effect here. You can imagine the incredible energy and violence of the impact that formed this magnificent structure. And again, this is something we can just appreciate a bit of from here on Earth. You can, with your binoculars or telescopes, you can find this area just peeking on the southwest rim of, or the southwest limb of the visible moon. There are several areas here that we would like to land in. There's an area called the Maunder Formation that's kind of a little bit down below where we're looking. And this is some of the actual impact structures, or impact ejecta. We have then some of the flooded mare areas like Lacus Veris, which is above, just to the right there. So keep going to the right with your cursor, just kind of a long, keep going a little further that area right there, Lacus Veris. So these are potential landing sites in the Orientale Basin. Okay, I think what we'll do now is we'll wrap up with a fitting grand finale, and that is the area that we have chosen to go with our next human landings on the moon, with the Artemis III mission, which will deliver the first woman and next man to set foot on the surface of the moon. And we're planning to send them to the vicinity of the south pole of the moon. And as Josh zooms in here, you'll notice that it gets kind of hard to make out the terrain. The shadows here are very, very deep and pronounced. That's because unlike at the lunar equator, where the sunlight can shine straight down, at the poles, the sunlight is coming in almost horizontally. And the rims of the craters, therefore, cast shadows, leaving the interiors of those craters in darkness. As a matter of fact, near the lunar poles, there are craters whose floors have not seen sunlight in well over 1 billion years. Because they are so very, very dark, they are also very, very cold. These are actually the coldest areas we have yet measured in the solar system, even colder than the surface of Pluto. And because they are so cold, it turns out these are also excellent areas for volatiles, such as water ice, to accumulate. And we have now demonstrated that there are indeed vast amounts of water ice sequestered at the lunar poles. Hundreds of millions of tons of water ice. Now, this could be an exceptional resource for us. That water ice could provide water for us to drink. It could be used as water making a building material. You can think of a lunar concrete to make structures. You break the water apart into its constituent hydrogen and oxygen. Use the hydrogen as fuel, the oxygen to breathe. Water can be worth more than its weight in gold on the moon. So this is an area of great interest to us. Again, it's highly obscured here, but Josh, you can bring up a better view, or I won't say a better view, but we can penetrate those shadows again by going to our laser altimetry. And so we will be depending on things like laser altimetry to help us plan our work in these areas. So another thing that makes the South Pole so particularly interesting is that it is very rugged, more rugged, much more topography than the North Pole. And so you have the deep, permanently shadowed areas where there may be accumulations of volatiles such as water ice, but then you also have mountain peaks that stand up and are in almost perpetual sunlight. That could be a great energy source. So you've got a resource of, or a potential resource of water ice and a potential resource of solar energy right next to each other. That makes this area particularly interesting. What we have to do, though, is determine the quality of that resource. Is this essentially an ore grade material? Something we do here on Earth with any kind of resource is we prospect it. We figure out how it is distributed. That's a key question. We don't know yet. And so we are planning to determine that with an upcoming mission that will come before the Artemis III mission. Artemis III is scheduled right now. We're scheduling 2024. But before that, we want to send a robotic rover called Viper. And Viper's job is to explore this area and to map out the distribution of volatiles, particularly water ice.
So if we've got a couple minutes to squeeze in some questions, is there anything that we found on the far side with the Chinese missions that has been perplexing?
Yeah, so the results are coming in there, and the Chinese have done something remarkable. They did land the far side of the moon, and they actually landed within that South Pole-Aitken Basin. So we're very much looking forward to seeing more of the data as it comes back. But this was really a spectacular achievement. And it could only be achieved by the fact that they also put relay satellites, because being on the far side of the moon, you cannot have direct communication with the Earth. And so they had to have relay satellites that were in orbit and around the moon and provided that communication link, that vital communication link for the descent and landing on the far side, as well as now for sending back the results. And we're looking forward to seeing more and more of what they are going to discover in the South Pole-Aitken Basin there.
That's fantastic. So we've seen a couple really awesome features for people to check out, even on their home computers. Right now, we are using the open space software, but if people wanted to do more moon exploring, Dr. Day, what would you recommend?
So, thank you for bringing that up, Josh. From your home, you can explore the moon and many other worlds as seen through the eyes of many different instruments aboard many different spacecraft. If you go to Trek, that's trek.nasa.gov, with your own browser, you can explore these worlds. You can explore the moon. You can explore Mars. You can explore asteroids. You can explore Mercury. You can, the list is growing. We've got moons of Saturn. We'll be adding to this list as time goes by. But go to trek.nasa.gov. We've got analytic tools so you can measure the size of features, the heights and depths of features. You can generate 3D prints. You can even create your own personalized virtual reality flyovers of features. So again, that's go to trek.nasa.gov.
So it's talking about just wandering around the moon and exploring features. I'm noticing something I think I've seen before, but is perplexing to me. Do you see some like chains of mini craters making sort of straight lines?
Right. We call these catenae, Catenae. And for the most part, the catenae are streams of debris, of ejecta, that are radial to a large impact feature. In this case, you can say they're radial to Mare Orientale.
That's
So these are
cool.
secondary craters. Imagine a bunch of rock being blasted out of that impact structure and those streams of rock slamming into the ground, forming these secondary craters. So
cool.
most of the catenae are in fact these secondary structures that are radial to actual large impact structures. Now there are exceptions. A great exception is one called Catenae Davy. And there what we think happened is that we are actually seeing perhaps something very similar to what we saw on Jupiter a few years back, where you had a comet Shoemaker-Levy 9, coming in and being disrupted into a series of smaller comets by Jupiter's gravity and then impacting one after another on the surface of Jupiter. We may see something similar like to that on the surface of the moon when we look at Catenae Davy.
Interesting. So main object falls, but there's a chain of material coming behind it that make
right. As that object comes in, it may be tidally disrupted by the gravity of the larger body that it's approaching. And so instead of hitting as one solid object, it hits as a chain of objects coming in.
That's fantastic. Well, I think we are reaching just about the end of our time, but Dr. Day, thank you so much for taking time to do our Cosmic Conversations. We really enjoy having you here, and we can't wait to have you back at the museum.
Thank you so much. It's been a pleasure. Take care.
And for everybody out there, stay happy, stay healthy, and tune in next time. We're going to have a lot more astronomy content coming next week. So until then, bye.
Bye.